What is a programming language, what is a program, and what is a programmer.
Great. All right, thanks a lot. I'll give everyone a chance to sit down. So I'm Ben Zorn. I work in the Research and Software Engineering group inside Microsoft Research in Redmond. And I'm here today to talk a little bit about my perception about the work I've been doing and what motivates me in my research agenda with respect to understanding potential users. So to start with that, I'm going to talk a little bit about my history so you get a little sense of where I come from and what I do. Just as an outline for the talk, the first part of the talk is going to focus on my understanding of how things are different now than they were, say, 20 years ago. But particularly, I think this is especially important to young people who are in this field because the future is not going to be like the past. I'm going to try to make the case that the future at this point is very different than the past, and we should think about that. The second part of the talk, I'm going to focus specifically on the work I've been doing with spreadsheets and try to argue that working with programming tools for spreadsheets is actually a difficult task and also a very important task. And finally, and we've already heard a number of the conversations about AI today, I'm going to focus a little bit on what I see the impact of AI is going forward on our field. And we've heard various things. We've heard the word software 2.0. People have said, forget it, we're not going to need programmers anymore. I'll speak a little bit to that topic. And I'm happy actually later after the session to talk about it more. I think it's a really interesting topic. Okay, so let's talk about my history. In 1989, I got my PhD thesis in working on garbage collection. And in particular, as I did that thesis, I was looking at the memory impact, the memory locality impact of garbage collection. And I did a lot of measurement. I looked at multiple programs. I looked at multiple techniques. I used box plots. I produced hundreds of graphs. This is actually a pretty challenging problem at the time, and lots of data. So fundamentally, even though I was doing research on garbage collection, I was really doing data science. And in particular, there's conclusions I reached in my thesis that were probably totally incorrect based on the data I had collected. And I'm going to talk more about that. I think we have to think carefully about what we do. Even every day in our research, we have to think about what we do and whether or not it's actually statistically significant. So let's step forward 10 years, and I started at Microsoft Research in Building 9, which they just tore down, but it was a great building. And at the time, you can think about what the computers looked like. So at that time, we had desktop computers. It was kind of nice to have a powerful desktop. We had laptops. The big computers, the things that people got excited about were these supercomputers. And Cray, this is probably one of the machines in a long series of Cray machines. In particular, though, it was renowned. It was a Blue Mountain supercomputer, and it had about 3.1 teraflops. So that computing at the time was like that. What were the developer tools like? Well, fundamentally, we had Visual Studio. It's still here, but we started with Visual Studio. And what people don't think about as much about Visual Studio is it really started with Visual Basic. And it was a transformation in the way that developers wrote code. And instead of writing individual lines of code, a lot of it was drag and drop components. So if you wanted to select a file in the file system, there was a component for that. You didn't have to go down to the level of the API and understand the OS, et cetera. That was a big innovation. At the time, we had Java. It was just beginning. It was really one of the early releases. We had JavaScript. I love this book about JavaScript. It's the beta edition of a book. So when you think about that, it's like, I'd like to upgrade my beta book. But anyway, it sort of gives you a feel for how quickly things are moving and how much impact these things eventually we're going to have. ECMAScript was only standardized in 1998. And it was just the beginning of a huge impact that JavaScript has had on developers and computing. Okay, so let's step into the world of data science, a different world than developers, and think about the tools they had. And in particular, there's a great tool that we all know and love, Excel. That's how it looked. It looked pretty similar to what it does today. We had some other tools on the horizon. In particular, when I did my thesis, I used S, which is a programming language designed by statisticians. It had a lot of support for visualization, but at the time it was basically a kind of a product that very few people knew about, and it eventually became R. So in particular, later, it really had a huge impact on the whole field of data science. Likewise, Python. Python at that time was version 1.6. I think it didn't have garbage collection at that point, which is kind of amazing to think. Again, these languages, they live for many years. You can see it started in about 1990, and it lived for many years before it actually became the thing that we know now. So a lot of these things do have a long ramp up and eventually have a huge impact. Okay, so let's step forward to 2019. This is the new building that I'm in now. And fundamentally, we can think about computers today and how they compare to computers back then. So in particular, we have our Apple, 11 phone. In that phone is actually a GPU, and I looked online. I tried to get a sense of the performance. It's about people estimate about 0.7 teraflops. So that phone in your pocket has 0.7 teraflops. Kind of crazy. We have things at the low end. In particular, there's a project Microbit, which is like a $5 microprocessor that allows people to learn how to program and how to understand computers. We get things like our doorbells now are computational. We have the Xbox One. That one, the Xbox One X, clocks in at 6 teraflops, which is twice what the ASCII supercomputer was back in 1998. And the NVIDIA computer in the latest Tesla was sort of considered to be around 30 teraflops. These are kind of not exact numbers anymore because it's not exactly a floating point, et cetera. But the bottom line is that your car has way more computing power than the whole world probably had in 1998. So think about that. Think about what that means about the developer experience. Oh, I forgot. Yeah, this is an important point. Okay, so forget the individual computers. This is a computer. This is the Quincy data center, the Azure data center in Quincy. There's 8 buildings. Each of these buildings is basically just full of racks of computers. And what we can do now is almost everybody is encouraged to harness the power of this to do new things with computers. Okay, and it's not just that it's available. It's actually easy to use. And so let's step into that. Let's talk a little bit about the developer experience. So we still have Visual Studio. It does more for you. It has some things like programming by example, for example. We have Visual Studio Code, which is platform independent. It makes it easy to basically code in any environment. But beyond the original tools that we had for developers, we have a whole new set of tools that are very powerful, and you probably all use, like GitHub. Right now, we have a way to consistently understand and share and to manage the versions of software. And it's just huge empowering because anybody that wants to can now go there, get what they want, download it, to make changes, push up the changes, et cetera. It really accelerates the cycle of development and sharing, et cetera, in the space. Likewise, Azure. As I mentioned, we have that giant building full of computers. Well, we actually have an interface that's quite powerful that allows people to just sit down, drag and drop a few things, make a few connections, and build a service in Azure very, very easily. And the tools are there to make that possible. And finally, beyond Azure, we essentially have this notion that now we have the cloud. We have a very easy way to move things into the cloud, to manage things in the cloud. We have Kubernetes. We have workflows around this whole process of building services, deploying them, debugging them, et cetera. And none of this existed in 1998. This is all new stuff, and we have good tools to help us do it. Not great tools, but good tools. Okay, so let's shift gears, talk about data scientists in 2019. Okay, this is dramatic. Here we have Excel. Okay, Excel is still there. It's a very powerful tool, but the reality is the user experience in Excel today is not all that different than it was 20 years ago. Likewise, we have RStudio. How many people use RStudio? Okay, so is RStudio as good as Visual Studio for doing development of R?
I use it sometimes, but mostly for command line.
Yeah, okay, command. So RStudio is a user, it's a UI. It gives you some convenience, but really it's very primitive relative to the kind of the things you get in writing other kinds of code. And similarly, Jupyter Notebook's actually a great innovation in the sense that it allows people who are doing these data science experiments to duplicate and reproduce effort and share effort. But fundamentally, the tool support in Jupyter Notebooks is relatively limited. And this is a quote from a data scientist. All the stuff regular developers take for granted, you move to a notebook environment, you don't get that. So basically, we're back in the old days with respect to the kind of tools available for data scientists. And so as a starting point, I want you to walk away with a couple things. Computers have evolved dramatically. The way that developers interact with computers has also evolved dramatically. And the people who aren't developers, who use computers, who want to get all that power out of the computer, they have not had their experience evolve dramatically. And we have to think carefully about what we can do to improve that. One of the things to point out here is that we're looking for AI, we're looking for ML and data science to deliver answers to harder problems. That's why all the discussion around AI today has been around how do we deal with security? How do we deal with adversaries? How do we deal with robustness, right? That's because we want more out of these systems. But the other side of that is the tooling, the kind of things that make developers productive and effective is not there for many of the people working with these systems. So I want to say, especially to broaden your view, and let me jump into the next step. So this is a call to action. So I think of professional developers, the pro dev community is well served. We've got lots, they've got tools, they've got interaction, they've got community that they use to leverage. But the grow dev community, and I think of this as all these people that are using computers every day who need that computer to basically do their job, who people are expecting more and more for you to deliver on, what's the trend here? Is this hypothesis true? Is this advertising campaign working? These are the questions that people constantly being asked. They use computers to answer them, and the tooling to help them answer those questions is not great. And so, this is my call to action. It's basically to think about those other individuals that aren't necessarily developers. And why is that? Well, first of all, there's a lot of them. There's one estimate 750 million Excel users. Okay, so how does that compare to the size of the Python community or you think, oh, there's so many Python users. Okay, well, maybe not 750 million. And so I think you have to ask yourself fundamentally, why is it that my research doesn't consider how these people are using computers? Just as an aside, is I think one of the challenges in our field has been that we focus on code. And maybe it's historical, maybe the semantics of code, we figured that out and it was so clean and beautiful. But the reality is that, this is a great thing with Wirth, right? So, data structures plus algorithms equals programs. That's it. That's all you need is data structures plus algorithms. And he missed this one fundamental point, which is if you don't understand the data, if you don't know where it came from, you don't know whether it's correct, if it has noise in it, your program is going to give you a bad answer. And none of the analysis of the code is going to tell you that. So this is a fundamental point that we have to understand as a community. So how do we wrestle with the fact that we have perfect code and really imperfect data? Okay? And how do we even know that we have imperfect data? Where's the thing that tells us that this is the wrong data to run on? Or that the place you got this data was an adversary that was trying to screw up your machine learning algorithm? Right? How do you know that? Okay, so that's an aside. I want to go back to spreadsheets. I gave them a hard rap because I basically said they hadn't evolved in 20 years. And that's not at all true, actually. If you look at the tools, you look at what people need and what they have. So for example, it used to be Excel was a single platform, it was Windows. Now you can get on any device. If you want to collaborate when you're working together in various documents, including Excel, you have collaborative editing. And this community knows about the work of Sumit Gawani on program synthesis and flash fill, and the idea that you can basically, from examples, from very small number of examples, infer the correct program in terms of string manipulation. And I encourage you to go and use it if you don't know about it. I'll demonstrate it for you if you want me to. And another item that's quite important is the notion of rich data types. So this actually appeared in Excel relatively recently, and it allows the cell contents to not just be some simple data types such as strings and numbers, but actually cells now can contain entire structures or arrays. And this is revolutionary in the sense that the Excel engine, the virtual machine, had to support this. It was a major engineering effort to plumb this through, and the fact that these are there now makes Excel a much richer experience. Okay, but, and this is a big but, and this is the transition to the second part of the talk. Despite the fact that we have these tools and we have so many users, et cetera, and we know that important decisions are being made. In fact, it's going ahead here. In fact, what we also know is that people make enormously bad mistakes in Excel. And one of the classic ones is this famous London whale. It was a JP Morgan trader that basically had an error in an Excel spreadsheet, and it turned out to sort of say, you should invest here, and he invested there and he lost like $9 billion. And and JP Morgan had to spend like $900 million in damages, and it was just a disaster. But it comes back to, it's like, well, what was the specification for that program that that had the bug in it, and why wasn't that being checked? There's all kinds of errors. You can just look it up online. This is one of my favorite errors. Is they discovered a couple years ago as basically biologists were looking at published results in biology, and it turns out that in that field, Excel is used often as a way to communicate the results. So in addition to your paper, you have an Excel spreadsheet that has documentation. And in that, spreadsheet, do I have it here? Let's see. No? Okay, it doesn't. In that spreadsheet, what the problem was that some of the gene names were things like sept1 and sept2. And it turns out that Excel automatically converted those things into calendar dates. And only after the fact did people notice that, in fact, in all their genetic data were a bunch of calendar dates that didn't make any sense. And so again, it's like, why didn't that jump out at people immediately when it happened? There's another one. This is apocryphal. You may have heard of this error. So Reinhart Rogoff were economists from Harvard. And they had a theory about economic growth and debt. And so they went and looked at many countries. Oh, sorry about this. They looked at many countries, and they actually measured the relationship between the debt the country was in and whether the country went into a recession. And I'll show you the spreadsheet, so we'll get to this later. But it turned out, and their recommendation based on their analysis was that if a country gets into too much debt, then it basically goes into recession. And so that is a justification for economic policies of austerity that say, hey, we're not going to let these countries go into debt. We're going to make sure that they pay it off. They don't spend anymore. And that, for example, was used to justify austerity in Greece. It was also used in the United States to justify a budget, big budget cuts. It turns out their analysis was flawed, and I'll show you why. So let's jump up a little bit. So we admit there are issues with Excel. So why is it that we don't have solutions? Why is it that we just don't obviously put the right tools in there? We're a programming language community. We're good at finding bugs, right? Why is it we don't just find the bugs in Excel and be done? So here's the problem. So first of all, Excel has more than just code. Like almost all our analysis looks at code, tries to understand well-formed semantics and syntax, and tries to find issues around that. But in fact, Excel contains code in the nature of formulas. It also has data. So what do you do when you try to understand that data? And finally, it has presentation. And the difference between C# or Python or whatever and Excel is that Excel, the presentation is a big part of the whole story. It's like it's intended to communicate from one human to another some kind of information with the assumption that that other person can interpret what's being shown. And here's an example. Basically people lay things out. They use bold. They have lots of blank spaces. They have, they understand that some of the words are meaningful to people, like net assets. What does that mean? Net liabilities. And the nice thing about this whole problem from a programming language point of view is, this is great opportunity for us. We have code, data, and presentation. We don't know how to deal with presentation in terms of understanding semantics. But somehow in that Excel spreadsheet is a semantics. There's an intent there. And the whole point of bug finding is to understand the intent and try to see a mismatch between intent and what was actually executed. But there are no specifications. There are no tests. The type system, at least until these rich types I mentioned, is very limited. And so, if you add a number, well, is it $1? Is it €1? What else? You have a set of users that are not developers, so you can't give them the traditional kind of feedback in terms of what's going on. You have to think about what their experience is. And then, and this is kind of one of the things that we discovered, even understanding where the table is on a sheet. You think, oh, a sheet is a table. It's it's rows and columns. That's a table. But in fact, people embed tables in all kinds of different ways into sheets, and recovering that information, what's a table, is actually not a trivial problem. So let me talk about Excellent. So Excellent is a project I did in conjunction with Dan Barrowy and Emery Berger. And the intent of Excellent is to understand the structure of spreadsheets on the assumption, that the spreadsheets capture some kind of regularity. So, people don't build spreadsheets that are totally irregular, just like they don't write programs that have lots of go-tos. And if we assume that, and we make assumptions that say if people break the regularity, then that might be a problem, then we can find errors. And so let me do a demo. And I'll start with a simple sheet, just so you have an understanding. So first of all, how many people know about the formula view in Excel. Formula view, anybody? Okay, a couple people. Now, see, this is a good starting point. So, for example, if I go over this cell and I click on it, up in the corner you see sum, right? So I can look at an individual cell and there's the formula bar and it tells me what's in there. But now, what if I want to know where all the formulas in that sheet are? How would I do that? I could like selectively sample. That's tough. Okay, it turns out Excel does have a built-in feature. It's control backquote if you want to know. And it does show you all the formulas in one view. And that's very powerful because now instead of like guessing at which of those values that I see on the sheet is a number and which is a formula, I can see it. It's pretty good. When you see it in this particular spreadsheet, you notice some weird things. You know, it's a little hard to spot, but there's some irregularities here. And the whole point of excellent is to say, you know, those irregularities, they shouldn't be something that you can sort of find if you look hard. It should be like, it should jump out at you. And so I'm going to use excellent. This is a built-in, it's a plugin for Excel. Emery Berger implemented it. And I just say reveal structure, and immediately a bunch of things jump out. Okay, so I'll walk through a little bit the UI here just so you understand what we're communicating. First of all, there's different colors, and there's two distinguished colors that you should understand. The gray color means it's a piece of data. It's not being computed. And not only is it a piece of data, it's actually being used. So it's a piece of data that's being consumed by a formula. Well, this is, the gray colors here, these values are all flowing into some formulas that are over here. So that's what that's telling you. If it's a piece of yellow, if it's colored in yellow, that tells you it's a piece of data that has nothing using it. It's not flowing into any formula. So for example, these cells here are all being computed, but they're not being used by any other formula. Okay, so that's the first part of the story. Now, what we really are interested in is the structure of the formulas. And what we do for the formulas is we use a different color for each formula type. And by type, what I really mean is the structure, the spatial structure of the formula. So a whole row of values that perform the same sum action over different columns will be colored the same type. But what you see here is in this particular case, you've got a cell that contains a formula that's different than the ones below it. And if I open up the formula view here, you can see that formula sums from B6 to E6, where all the other ones below go from B7 to D7. So it's an off by one bug in this particular sheet, and in fact, that's an error in the sheet. Just to sort of help understand the whole picture with excellent, the second part of excellent, beyond the coloring and the sort of the visual patterns that people can understand by looking at it, we have an analysis that tries to find irregular rectangular structures and looks for fixes that will actually make the entropy of the sheet lower. And this is work that was published in Uppsala, but in particular here, if we look at what it calls suspicious cells, then you see it highlights this group of cells, which are two adjacent rectangles, that if they were to be merged, it would decrease the overall entropy of the sheet. And so that's a suggested fix that a human then can go look at and try to figure out. Okay, so that's an introduction to excellent, but let me show you the more interesting case. So this sheet is the Reinhart Rogoff spreadsheet. And in particular, the thing to note here is that this is the summary page. You see on the left here a list of countries. This is the US down to Australia, and you see the dates. It basically covers, this is historical data of the countries and their economic to other sheets. There's a lot of data in the spreadsheet. This is a lot of work that people manually constructed, basically laboriously, to come to this conclusion about economics. Okay, look at it. It's like, well, I don't know exactly what's going on. I don't, sheet what's going on. So if I hit reveal structure, okay, yes, there you go. Okay, if I hit reveal structure, this is what happens. So we see the colors again, and the important thing to note here is that this range of cells is yellow and this range of cells is gray. Now you ask yourself, why would they, in the summary sheet, why would they have a bunch of values that come from some other sheet maybe, come here and then are ignored, right? What is going on there? Well, here's the problem. their formulas were all wrong. So every formula down here that's green actually only measures the information from the first 15 countries. It ignores 5 countries. And as you can imagine, that might throw off your results. And in fact, it does. If you add these countries, which are Australia, Austria, Belgium, et cetera, you actually get a totally different result in your analysis that says that going into debt does not cause recessions, essentially. And the beauty of this approach that we're providing is, you think about the time that people put into the laborious effort to have this spreadsheet. And then without this tool, they made the mistake of going to the whole world and saying, hey, we got this result. Isn't this exciting? And in fact, what they actually had was a big mistake, a big black eye. So that tells you, that's sort of the story about Excellent. It's open source, so you can use it. You can try it out. Please contact me, and I'll point you to it. Let me just continue. Okay, so I'll step through this. I talked about this. Now let me talk about the second approach we've taken to understanding spreadsheets. As I mentioned, spreadsheets have this element which is quite difficult to approach because it contains things that are hard to enumerate. Just like finding a face in a picture is a hard problem. Basically finding a bug in a spreadsheet, you could consider it a hard problem. And so we ask ourselves, if I can find a person in a picture with machine learning, can't I find a bug in a spreadsheet? And in particular, the first effort we took in this space was a project called Melford, and there's a tech report that describes it. But we used neural nets to find errors in spreadsheets, specifically errors where the spreadsheet should contain a formula, but for some reason, the person who wrote the spreadsheet had a value there. So they didn't compute it, or they computed it by hand. They didn't use a formula. And this is an example. Right here, you see total. This is clearly the sum of these. But this value, for whatever reason, is not being computed. It's just a value. And the whole idea of Melford was, if we train a sheet and we show it many, many examples of patterns of formulas, and then we show it this, it's going to come back and say, this is something suspicious. You should fix this. So the idea with Melford was to apply deep learning to spreadsheets, use lots of spreadsheets as training, and then from that we can actually make informed decisions and conclusions about the spreadsheets. So we started with bug detection, but as part of bug detection, we realized, well, we really need to know where the tables are. It's very useful to know where the tables are. That really is a structure that's embedded into the sheet. And it turns out that the algorithms to find tables were not very good. So if you go right now to Excel, I'll show you, and you hit Control-T, that's like the built-in thing that finds a table around the current cell, and it has definite limitations. And you can see these tables are an example of why it's hard. It's because, in fact, there's probably, most people would conclude that there are 2 tables here, but there's lots of blank cells. There's highlighting that sort of helps you understand what the boundaries are, et cetera. But how would you write code that would analyze these various things? And so what we decided was, let's apply machine learning to this problem. We're going to use the insights from computer vision, but we have a challenge, which is we don't have a lot of labeled data. So in this particular case, it would be great to have 100,000 spreadsheets where somebody's already told you exactly where the tables are, but we don't have that. And so we had this challenge. Well, we could do labeling ourselves, and in the end, we ended up with hand labeling spreadsheets to show where the tables are, and using Mechanical Turk. But we took a different approach to the problem. Instead of saying we want to know where the table is, we said, well, can we find the corners? So we're going to look at a specific cell, and we're going to ask, is this cell a top right corner? Is it a bottom left, et cetera? And this process of finding the corners is actually, we can get much more data, because every sheet now is going to give us many instances of cells that we can then use as training for a model. So what we do is we take the sheet, we basically extract all kinds of information, and this goes to why machine learning and AI has this benefit, is that we didn't have to do a lot of feature engineering. We just said, look, let's look at the font, let's look at the bold, right? Let's look at the style, let's look at what type of value it is. And from that then, we have these layers, we can encode those layers into abstract layers with 51 abstract layers And then, of course, this is where we apply the sort of the traditional convolutional neural network approach, where we look at a particular cell, we look at a region around the cell, and then we train a model that says, given the context, in this case a 15 by 15 rectangle around the cell, what can we conclude about that cell? What do we know? And essentially, we try to predict the corner probabilities. And that's what the model tells us, but we're not done because we still need to say, well, where are the overall tables? And so in addition to this DNN, we actually use a Bayesian inference to figure out the best pairings of corners to give us the tables. And I'll just show a little bit to sort of give you a sense. Again, if you want to see this in action, I have a working demo, a working prototype that I can show you offline. But this is an illustration of the debug mode. You know, we heard a lot about debugging neural networks. Well, this is a hard problem, and we had to implement this as part of our implementation to understand what was going on. So in the debug mode, we're not doing the whole table identification. What we're doing is we're identifying for each cell what the signal is from the neural network for that cell. And the different colors denote different corners. So blue is bottom right, pink is top right, etc. There's actually 6 because we also look for the headers of the corners, the corners of the headers. You can see here, like for example, this cell, it thinks maybe is a bottom right, but it's not as strong a signal as this one. Okay, and that's kind of what you end up with. You end up with sort of imprecise information that you then have to do your best guess to stitch together. Okay, once you have that, you can run, as I said, the inference to try to find the most likely tables, and you find these 2 tables. And that's Jura. That's Project Jura. That's joint work with Alex Polozov and Saswat Padi, who is our intern. So this is a very exciting domain. And one of the things we haven't exploited to a large degree is natural language understanding. So when I talked about the encodings of the cells, what I didn't say, and what we haven't done yet, is encode the words in those cells, right? And we already have very powerful word embeddings like BERT, and even word2vec could be used. But the idea is that once we have things like the fact that this word is total, that's going to be a very powerful signal to infer other things about the table. Like, for example, if the word is total, then there's a high likelihood that there's a bunch of sums on that row, for example. But there's all kinds of interesting signals. So we have, obviously, the visual, which is what the human consumes. We've got the natural language, again, trying to understand what the legends are, what the headers are, et cetera. And finally, there's code. I mean, this is the cool thing about this, is that not only do we have all this spatial information, we actually have dependence information because all the different formulas depend on each other and on the data. So this is, I put this out there to everyone in our community. This is just as important a problem as understanding, say, a paragraph of text. It's an easier problem in the sense that we have a lot of interesting signals that we don't have when you have a paragraph of text. And more importantly, there's also program stuff in there. So it's like we can connect the analysis to actually program analysis and semantics, which is, again, it's a unique opportunity. Okay, so let me just shift a little bit here and talk about broadening the view. So, there's a lot of spreadsheets in the world. There are a lot of spreadsheet users, but that's not the end of the story. In fact, tables are everywhere. So if you go to, data.gov, you find hundreds of thousands of data sets in different formats, CSV, Excel, zip files. But there's also, tables on the web. Like many web pages have tables. And again, there's information. In this case, you see like World Cup scores. And I might want to ask questions like, historically, is Mexico better than, Brazil in the World Cup, right? And my hypothesis might be that Mexico is better, and then I could actually perform a statistical test to figure out, whether it really is. So another source of lots and lots of data on the web in the form of tables is annual reports and financial reports. This is a case where people had the data in some kind of computational medium, like a spreadsheet or a database, but then they published it, and they published a document which is just numbers. And it's interesting because you assume that those numbers actually add up, right? That if you do the math. But if you look at spreadsheets, it's so easy to cheat in a spreadsheet. I mean, any cell you want, you can just add a constant to that, and it is part of the formula. And it's unless you actually open up the view and look at the formulas, you can't see that that's happening. There's actually a paper about people who audited spreadsheets that recorded information about imports in Great Britain. This is about in 2000, around 2000. And they found that there was systematic errors that accounted for about 13% of all reported value of imports. So 13% of the entire import value was incorrect. And they, surprisingly, they were in the favor of declaring, indicating that there was less imports to be taxed. So, you wonder, is that an error or is that intentional? Okay, so let me just segue into T. So as I mentioned, there are tables everywhere. T is a programming language, and it's a particularly targeted programming language for an audience of users that are people who have data in a table. And with T, all you need is a CSV file. So it's basically, a lot of people have those things. I mean, most of you probably have those things when you're about to write publish a paper. And the question you have with that data in a CSV file is my benefit, let's say I did technique A versus technique B, is technique A statistically significantly better than B, right? So that's a hypothesis. And the question is, well, with the data you have and the assumptions you have on that data, like, is it, what tests do you perform to show, that it is, that A is better than B, and with what significance? And, there's all kinds of things around p-hacking, so people try to find the test that gives the most advantage, et cetera. But this is how T works. Essentially, you just specify where your data comes from, what the variables are. That's essentially what the columns are. What kind of data? So is it categorical? Are they dependent variables, independent variables? You talk a little bit about the study design. But the most important thing is you make a hypothesis. So you basically say, I want to know, is category A better than category B? And what happens with T, which is a really major advance for the people doing this, is instead of guessing maybe the t-test is appropriate here, or maybe it's a student's paired t-test, what T does is it has an understanding of all valid statistical tests. It understands what constraints they operate under, and then it does a SAT solver solution that finds all the tests that map the constraints that the user has expressed. And so instead of guessing that this is the best test, and it may be that you don't even know what the best test is. How many people here know all the different statistical tests? Instead of doing that, it gives you the best test and it gives you the result for it. And again, this is open source. You can install it as a Python package, and you can get it at tlang.org. So again, this is reaching out to a much broader audience than your typical programmer, right? This is people who have data, and there's a lot of those. Okay, so the next part of my talk, I want to focus on this AI thing. So we've heard a lot. We've heard about Software 2.0. There's all kinds of measures of how much data there is in the world, but this is one, IDC Data Age 2025. Michael Dell tweeted this. It basically shows this is the amount of data created in the world up to 2025, and you can see this is like 2019 right here. So whatever we have right now, by 2025, we'll have 4 times as much. Okay, and that's a lot of data. I guarantee that. This is kind of a joke, but the point here is the ratio of code to data in the world, there's like no code. By most approximations, it's all data. Okay, so that sounds pretty good, right? A lot of data. How can we argue? In fact, this is a pretty old article, but it was an article, a cover of Wired. Is it the end of code? Right? Are we done? And we heard that twice this morning, by the way. Okay, so think about that. There are seriously influential people in this field saying that code is dead. So that might be a wake-up call to you programming language people. So let's talk a little bit about AI tools. I mean, this is kind of fun. I don't know if you've seen it. It's a playground.tensorflow.com. It essentially allows you to create little neural networks and then run them. It's good. It's good for education. Not really that useful for developers. This is better. This is actually pretty interesting. So they have this thing called the annotated transformer. In this field, people have actually worked hard to take models that are published as Python. So they have papers, they have models. And this actually, they made a literate version of one of the papers so that you could step through the individual parts of the paper, this is about transformers, and execute the code to make sure that it does what you want, or you could tweak it, et cetera. I think that's great. I think the notion of these notebooks and live notebooks is very powerful. And you can see, this is another example of the kind of embedding of code and some kind of literate function that gives you this opportunity to visualize. But again, these tools are extremely weak. Okay, when we step back and say, here's Windows, and we want to find bugs, and Microsoft runs Sage, which is an internal fuzz testing tool, and it runs over 1 million or 10 million lines of code. That's serious tools, okay? And I think the question becomes, for these kinds of projects, like what are the equivalents of that, right? What kind of really heavy lifting can programming language technology do to help build good models and find bugs in models? And it's not just us. This is Christopher Wray at Stanford and this Snorkel project. And basically he's saying, we think that the future is about, everything is about taking data, converting it into programs. And what we want to do is make it easier. So we're going to make it easy to get that data. We're going to make it easier to label. We need to understand what it means to label, or can we clean up the data after we have noisy data, et cetera. These are all key questions that we should be asking. It's not just an issue that the AI or that community should be asking. It's actually questions that we should be asking. Okay, so let me wrap up. You could sort of be discouraged. You could say, hey, maybe it really is true. Maybe the data will just overwhelm the code, and eventually it'll all be data. So I personally think that is just it's nonsense. The first thing is AI itself is software. Fundamentally, we know that these models execute, and there's just a lot of software in there, but they're not doing everything. There's a lot of code around them, so that's the first issue. The software is not going to go away. It's going to be part of the story. I think this is really interesting. So this is Microsoft. Microsoft wants to really be very clear to the world about what it thinks about AI and how AI affects its business. Microsoft is fundamentally a software company. And here's what they say. These are the principles that we're going to uphold. Fairness, inclusiveness, transparency, reliability and safety, security, accountability. Well, you may ask yourself, why is that about AI? That's just about software, right? Would any company say, oh, none of those principles are important for all our software? But why do they say that for AI? It's because AI doesn't give you any of this stuff now. We're so far behind with AI that they have to get out in front of it and tell you that that these are key things that we're going to deal with. And hey, by the way, we don't know how to do it, right? Nobody knows how to make it completely reliable or completely fair. That's why it's such a great problem. And in fact, I think the key takeaway here is, as a community, we've developed incredible technology to think about really large-scale programs and code. And let's think about how we can take all those great ideas and apply it to this new problem. It's a different problem, but we have very many of the same. And we've seen work here that's discussed how we might do that with verification, et cetera. And this is another part of the story, which is that it's not just about AI is still software. It's also about there's more and more interesting problems. It's like the number of interesting things that we use software to do has increased. It's really enriched our ability to impact the world. This is a slide by Ed Lazowska. And it's he talks about this in terms of the impact that computer science has been having, and how we started with the core things like programming languages and operating systems and architecture, hardware. But really now we're talking about a lot of different impacts in many different fields. Things like health or energy or transportation, right? And this is one of the reasons I'm giving this talk, is because I want to encourage you to not think it's all about helping other programmers or helping other mathematicians. It's really about the people building transportation systems. It's people building energy efficient data centers. It's people who are trying to figure out how to cure Alzheimer's or whatever. There's so many different ways that the technology we build impacts everyone's lives now. We have to be aware of that. Okay, so just in conclusion, the questions. What is a program? Well, today I said, hey, a program can be a spreadsheet. It can be examples. We know that. It can be hypothesis and annotations on a data set, or it can be 100,000 labeled images. All of these constitute something that you put into a system, and what you get out is essentially a program, or more importantly for the people that that want to use these programs, an answer to their questions. I would argue everyone is a programmer, certainly hundreds of millions of people, and we shouldn't forget about those people. And finally, I think the key questions in our sort of future here are, how do we move the great investments we made in technology we have that help developers now, professional developers, move into a world where those things are enabling many, many people, not necessarily developers, using computers. And so I call it grow dev, just as a term, but the idea is to think about those people, understand what they're doing. One of the big barriers here is not knowing what people need. Like, how many people know what the day-to-day life of a commercial data scientist is? Like, what is their process? What are the things they worry about? Like, what are the obstacles that make it harder for them to do their job? Those are the kinds of questions you could ask. And certainly one of the nice things about this work we did with deep learning was it gave me a direct view on what the process of developing with machine learning and DNNs are. And it is really painful, let me say. Okay, it's like when and actually excellent in the work that we did with Jura are great contrasts, because with excellent, if we found a bug, we'd say, okay, let's go and let's change the code. Like 20 minutes later, we would have something that would fix the bug. With a deep learning model, first you have to ask, is it a bug? And then if you think, yeah, maybe it is a bug, then you have to ask, okay, do we need new training data? Do we need to retrain? I mean, and then anything you do is like, oh, well, that's going to take a day. Right, so any kind of development process where there's a lot of uncertainty and that getting a turn of the crank is one day is actually very painful. So anyway, and just as a final note, I want to say, think about human interaction. This is not just about semantics. It's not just about logic. It's really about people and how people interact with computers and and with each other. Right. So fundamentally, one of the great things about AI is it gives us a hook into trying to get more than just the things that are easy to encode, like logic. Okay, so this is a thank you, just to say these are all the great people that I work with, and I'm really grateful for. A lot of the work is their work. I have a Twitter account, so if you like some of the things I say, you can follow me. And I just want to also put in a plug. Tomorrow, I'm still here. I'm going to give a talk in, I guess, Lawson, 3102 at 11 a.m., and it's about the Computer Community Consortium. And if you don't know what that is, come to my talk. If you want to know what it is, this is a little bit of the story. It's about an organization that thinks about the future of computing research, and it's a grassroots organization, and it needs your input as well. So with that, thank you. Oh, come on.
Okay, since no one else jumped in front of me, I'll ask you this. I heard recently Simon Peyton-Jones talk about educating young people in computational thinking instead of programming.
Yep.
Right? I think that dovetails closely, nicely with what you're talking about, and I wonder if you have any thoughts on that.
Thank you. That's a great question, and actually totally, absolutely on the mark. So let me say a couple of things. I think Simon is totally right. I really believe that we greatly underinvest in teaching young people about computing related things. And so I'm really proud of work that's being done inside the RISE group, which is this project called Make Code. Make Code, if you go to makecode.org, is it? Or yeah, anyway, it's basically a tool. It's actually a way to program small devices, and it's being used in many schools. It's, there's a whole curriculum around it. There's many different devices that plug into it. And that's really about coding. And it's a great sort of reach, and it's work, Tom Ball directed it. But I've had these conversations with Tom, which is along the lines of, sure, it's great to teach people about code, but what about, just think about data, right? How good is the education for young people around reasoning about data? And they're so important questions, like, where did this data come from? What does it mean to be statistically significant? Why is it that they didn't use 0 on the y-axis, right? Such a basic question, but every time you see a graph, you should ask yourself that, right? And so I think I think it's a tragedy that we don't teach statistics, reasoning about data, thinking about data and code together into young people. I totally agree. Thank you. Okay, I'm available afterward, so you can see the demos if you want to see them.
Thanks, man.